NENOMATICA, where mathematics meets YouTube excellence. In this lesson, we will solve floor function equations using the definition. We will follow a precise 3-step algorithm and apply it to an example. We will now walk through a complete example, step by step. Solve the equation, floor of 2x minus 1 equals 4. We begin with the definition. If the floor of f of x equals n, then n is less than or equal to f of x, and f of x is less than n plus 1. Step 1. Identify the integer n. Here, the right side is 4, which is an integer, so n equals 4. Step 2. Apply the definition. Replace the floor with a double inequality using n equals 4. That gives 4 less than or equal to 2x minus 1, and 2x minus 1 is less than 5. Step 3. Solve the double inequality for x. First, add 1 to all 3 parts. Then, divide everything by 2 to isolate x. Let us visualize the solution on a number line. A closed point at 2.5 and an open point at 3, with the interval shaded in between. Therefore, the solution set is all x in the interval from 2.5, inclusive, up to 3, exclusive. Our plan is to use the property that floor of x plus an integer k equals floor of x plus k, then simplify and split into 2 cases, when x is an integer and when x is not an integer. Step 1. Use the integer shift rule. Floor of x plus k equals floor of x plus k for integer k. Apply it to each bracket x plus 3, negative x plus 2, and x plus 1. Now rewrite the equation with the integers moved outside the floors. Combine like terms carefully. Move all floor terms to one side to isolate them. Step 2. Case 1x is an integer. For integers, floor of negative x equals negative floor of x. Substitute into the equation 3 times floor of negative x minus floor of x equals negative 7. That gives negative 4 times floor of x equals negative 7. So floor of x equals 7/4, which is not an integer. This contradicts the definition that a floor value must be an integer. So there is no solution in the integer case. Step 3. Case 2x is not an integer. Then, floor of negative x equals negative floor of x minus 1. Substitute into 3 times floor of negative x minus floor of x equals negative 7. We get negative 3 floor of x minus 3 minus floor of x equals negative 7. Combine like terms to get negative 4 floor of x equals negative 4. So floor of x equals 1. Step 4. Interpret floor of x equals 1. By definition, floor of x equals n if and only if n is less than or equal to x, and x is less than n plus 1. So floor of x equals 1 means 1 is less than or equal to x, and x is less than 2. In this lesson, we will solve a floor function equation step by step, exactly following a clear sequence of rules and transformations. Our goal is to find all real numbers x satisfying the equation. Floor of x over x plus 1 plus floor of 1 over x plus 1 equals 1. Step 1. We rewrite the fraction x over x plus 1 by adding and subtracting 1 in the numerator. That is, x equals x plus 1 minus 1. Substituting, we get floor of the fraction x plus 1 minus 1 over x plus 1 plus floor of 1 over x plus 1 equals 1. Step 2. We split the fraction. So x plus 1 minus 1 over x plus 1 equals 1 minus 1 over x plus 1. This gives floor of 1 minus 1 over x plus 1 plus floor of 1 over x plus 1 equals 1. Step 3. We now apply the floor property. Floor of n plus a equals n plus floor of a when n is an integer. Here, n is 1, and it was negative 1 over x plus 1. So we obtain 1 plus floor of negative 1 over x plus 1 plus floor of 1 over x plus 1 equals 1. Step 4. We subtract 1 from both sides to isolate the 2 floor terms. That gives floor of negative 1 over x plus 1 plus floor of 1 over x plus 1 equals 0. There is an important identity here. Floor of a number plus floor of its negative equals 0 if and only if the number is an integer. Therefore, 1 over x plus 1 must be an integer. Let 1 over x plus 1 equal k, where k is an integer. Step 5. Solve for x. Since 1 over x plus 1 equals k, we have x plus 1 equals 1 over k. Also, 1 over x plus 1 cannot be 0, so k cannot be 0 and x cannot be negative 1. Therefore, x equals 1 over k minus 1, where k is any non-zero integer. As a quick intuition for the identity, when a number is not an integer, its floor plus the floor of its negative equals negative 1. Only when the number itself is an integer do the two floors add to 0. That is why 1 over x plus 1 must be an integer here. Final answer. The full solution set is x equals 1 over k minus 1, where k is any non-zero integer. Example. We will solve the equation. Floor of x plus floor of 2x plus floor of 3x equals 12. Our goal is to follow a clean, step-by-step method to find every x that satisfies this equation. Step 1. Use a key property of the greatest integer, or floor, function. For any natural number n and any real x, n times floor of x is less than or equal to floor of nx, which is less than or equal to n times floor of x plus n minus 1. Now we will apply this for n equals 1, 2, and 3. Step 2. Sum the left sides, sum the middles, and sum the right sides of those three inequalities. This gives 6 times floor of x is less than or equal to the sum, which is less than or equal to 6 times floor of x plus 3. Step 3. Substitute the given value. Since the sum of the three floors equals 12, we place 12 in the middle to get 6 times floor of x is less than or equal to 12, which is less than or equal to 6 times floor of x plus 3. Step 4. Solve the compound inequality for floor of x. From 6 times floor of x less than or equal to 12, we get floor of x less than or equal to 2. From 12 less than or equal to 6 times floor of x plus 3, we get 9 less than or equal to 6 times floor of x. So floor of x is greater than or equal to 3 halves. Combining these, 3 halves is less than or equal to floor of x less than or equal to 2. Since a floor value is an integer, the only possibility is floor of x equals 2. Step 5. If floor of x equals 2, then x lies in the half open interval from 2 to 3. Now the original equation becomes 2 plus floor of 2x plus floor of 3x equals 12. So floor of 2x plus floor of 3x must equal 10. Given x is between 2 and 3, 2x is between 4 and 6. So floor of 2x is either 4 or 5. Also, 3x is between 6 and 9. So floor of 3x is 6, 7, or 8. The only way to total 10 is floor of 2x equals 4 and floor of 3x equals 6. These give the ranges. For less than or equal to 2x less than 5 and 6 less than or equal to 3x less than 7. Converting to x, that is from 2 to 2.5 and from 2 to 7 over 3. The intersection is from 2 to 7 over 3. Final result. The solution set is the half-open interval from 2 to 7 over 3. Recap. We bounded each floor term by a multiple of floor of x, summed the bounds, substituted 12, solved for the only possible floor of x, which is 2, then intersected the precise ranges for 2x and 3x to obtain the interval from 2 to 7 over 3. In this lesson, we will solve the floor function equation. The equation is floor of x plus floor of 3x plus floor of 5x equals 9. We will use a key property of the floor function. For any natural number n and any real x, n times floor of x is less than or equal to floor of nx, which is less than or equal to n times floor of x plus n minus 1. Let's apply it for n equals 1, 3, and 5 to each term of our equation. Now, add the three inequalities side by side. Left with left, middle with middle, and right with right. This gives 9 times floor of x is less than or equal to floor of x plus floor of 3x plus floor of 5x, which is less than or equal to 9 times floor of x plus 6. Since the problem states that the middle sum equals 9, substitute to get 9 times floor of x is less than or equal to 9, which is less than or equal to 9 times floor of x plus 6. From 9 times floor of x less than or equal to 9, we get floor of x less than or equal to 1. And from 9 less than or equal to 9 times floor of x plus 6, we get floor of x greater than or equal to 1/3. So 1/3 is less than or equal to floor of x, which is less than or equal to 1. Because floor of x must be an integer, the only possible value is 1. Therefore, X lies in the interval 1 to 2, including 1 but less than 2. Substitute floor of X equals 1 back into the original equation. In this example, we will solve a floor function equation step by step, matching each algebra move to a clear visual. The problem is the floor of x minus 1/2 plus the floor of x plus 1/2 equals 7. Step 1. Rewrite the constant. Notice that negative 1/2 equals 1/2 minus 1. So we can rewrite the first floor term as the floor of x plus 1/2 minus 1. Step 2. Apply the floor property. For any integer n, the floor of a plus n equals the floor of a plus n. Here, n is negative 1. So the floor of x plus 1/2 minus 1 equals the floor of x plus 1/2 minus 1. Substituting, we get two identical floor terms and a minus 1. Step 3. Combine like terms and isolate the floor expression. Two copies of the floor of x plus 1/2 minus 1 equals 7. Move the minus 1 to the other side to get 2 times the floor of x plus 1/2 equals 8. Now divide both sides by 2 to get the floor of x plus 1/2 equals 4. Step 4. Use the definition of the floor function. If the floor of a equals n, then n is less than or equal to a, and is strictly less than n plus 1. So 4 is less than or equal to x plus 1/2, which is strictly less than 5. Subtract 1/2 across the inequality to get 7/2 is less than or equal to x, which is strictly less than 9/2. That is the final solution set. To visualize the answer, place it on a number line. We draw the interval from 7/2 to 9/2, including 7/2 and excluding 9/2. Final answer. The solution set is all real x, such that 7/2 is less than or equal to x, and x is strictly less than 9/2. In this lesson, we will solve a floor function equation, and then find a digit sum. Our goal is to solve for x in the equation. 4x plus 25 equals the floor of 20 times the square root of x, and then compute the sum of the digits of 100x. Let's start by writing the equation clearly on screen. Step 1. Notice a perfect square pattern on the left. We can write 4x as the square of 2 times square root of x, and 25 as 5 squared. This sets us up to complete the square. Step 2. To complete the square, we want the middle term to be minus 20 times square root of x. We subtract 20 times square root of x on both sides. Now, the left side becomes a perfect square, 2 root x minus 5 quantity squared. Step 3. Compare signs. A square is always greater than or equal to 0. For the right side, recall a key fact about the floor function. Floor of u minus u is always less than or equal to 0 and greater than negative 1. Let's visualize that with a number line for u equal to 20 times square root of x. Since the left side is non-negative and the right side is non-positive, the only way they can be equal is if they are both exactly 0. Step 4. Solve the perfect square equals 0. 2 times square root of x minus 5 equals 0. So 2 times square root of x equals 5, and square root of x equals 5/2. Therefore, x equals 25 over 4. Now check the floor condition. 20 times square root of x must be an integer. At x equals 25 over 4, 20 times square root of x equals 50, which is indeed an integer. Step 5. Now compute 100x and the sum of its digits. 100x equals 100 times 25 over 4, which is 625. The digits are 6, 2, and 5. Their sum is 13. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.